Okay, here we go. Back to business. All right, here we go. So to recap, I didn't get that recording. Connor, you good over there? Good. You guys good back there?
Yeah.
Good back there? All right. So we're looking at these sets. Each time we build outward from the inside set, we're filling a gap. So as we said, natural numbers have a gap. The whole numbers fills a gap by adding 0. Integers fills a gap in the set of whole numbers by adding negatives. Rationals fill a gap that we have with integers by adding fractions. And then finally we get up to, that seems pretty good, but what if we want to solve a simple quadratic equation like x squared equals 2? What's the only step we really have to do to solve this? Square root. So I get x equals what? Plus or minus the square root of 2, but the square root of 2 cannot be written as a fraction. So the set of rationals has a gap there. What do we need? What do we got to add? Well, yeah, I mean we're going to push out. We're going to push out to all the real numbers. But what was left behind by just the rationals? There was a gap there. Irrationals. I've got to add another set called the set of irrationals to fill that gap, right? So if I get real numbers that can't be written as a fraction, well, I need those two. So we added this other set called the set of irrational numbers, and that seemed to do the trick, didn't it? Right? Then we had pretty much everything we needed, and we haven't had any problems, right? Okay, well, let's try a sample problem here. Let's try this guy. So what's going to happen here if I try to solve this thing? I mean, let's go. You tell me what to do to solve this. Let's go through the steps. We'll see. Add 4.
Yeah.
If I add 4, I get negative 2 times the quantity 4x plus 5 squared equals 18. Okay, good. Now what? Divide by negative 2. You guys get this. Piece of cake. Okay, now what? Okay, well I'm gonna square root though to get the x by itself. Agreed?
Yeah.
Okay, you might see some issues coming up, but the step is to square root.
What's our issue here? Unless it's not a real number. That.
Look at it. Problems. Okay, so what are we gonna do? We had an issue, right? We said earlier in the year, we've said this multiple times, there's a couple things we can't do for real numbers. We can't divide by 0, and I can't take the square root of a negative number, and that's true. So in other words, the set of real numbers fails us here, right? The set of real numbers has a gap, because this does have a solution. It's just not a real solution. So phone should be away. Right. So the set of real numbers, we gotta add something to fill in that gap, because there is a way we can handle this. Remember, we have a property for square roots, and I've mentioned this earlier. We haven't done a lot with it, but what do I do with something like that? How can I rewrite the square root of a product, the square root of a times b? Yeah, those are equal. Okay. How could I apply that here to the square root of negative 9? What could I break the square root of negative 9 up into?
But we're still wanting to be negative to satisfy the fact
It is. You're right. It is. So let's at least separate the problem from the part that's okay, right? So the square root of 9 we can deal with, but the square root of negative 1 isn't so good. So if we break this up into a part that seems okay and a part that's we're not sure about, we can get an answer. The square root of 9 is 3, right? So that part's okay, but what about that part? Square root of negative 1. That's not a real number, right? That doesn't exist in the set of real numbers, but it does exist. So here's what we do with that. we're going to define a new number called I, which is equal to the square root of negative 1. Why do we call it I? Because, unfortunately, the name of this is the imaginary unit. The imaginary unit I. So it's called, now ignore the name. Ignore the name. Imaginary is not a good name for it. It makes it sound like it's unimportant or it doesn't work. Or that it's not real in some way. It's just like some goofy imaginary thing. Or something. But it's not. It's very useful. It actually is a number that we use a lot. It's just not a number we use to count things. You've never used it before because everything we've done, believe it or not, really is just some more complicated than others, but everything we've done could be thought of as counting something to this point in your math careers. So we're not going to count stuff with this, though. We're going to do something different. It does exist. We call it I. And so we would write this as 3i is our answer. Now we have to put a plus or minus in there when I square both sides, right? So we get plus or minus 3 times I. Let's push on and finish this. Okay, I know it seems a little strange, but we can keep going. As long as we allow ourselves to use this different kind of number, that involves I, the imaginary unit I. We call this an imaginary number. Then we can finish. What are the last 2 steps to isolate x? Subtract 5. Good. So if we subtract 5, remember we always put that in front of the plus or minus when we got 2 terms like that. And then the last step, we divide both sides by 4. Now remember what we did, even, we've actually already done this. If we ended up with solutions, something plus or minus something else, if those 2 terms didn't combine, remember how we handled that. Instead of having a common denominator, we just divided each term separately, right? So we'd end up with x. We're going to divide that one by 4. So those cancel, equals negative 5/4 plus or minus 3/4 times I. So there's 2 separate answers there. There's the answer either x equals negative 5/4 plus 3/4 I, or x equals negative 5/4 minus 3/4 I. Those are legitimate answers. Okay? Those are just what we call complex numbers. So we have to add something to our set that we started with, right? We started with the idea that everything was a real number. That wasn't enough, though, we find out. We need something else. We need to be able to take square roots of negative numbers also. And so we expand the set of real numbers into the largest possible set of numbers, which is called the set of complex numbers. Real numbers are just a subset of that set. All real numbers are complex numbers, but there are other numbers that are complex that aren't real. Okay? So we'll get back to this picture in a second. So all complex numbers can be written in this form. A plus B times I, where A and B are just regular real numbers. Okay? But I is not. Remember, I stands for the square root of negative 1. Okay? So we call the A the real part, and we call the B the imaginary part, because that's the part that's being multiplied by I. And usually, instead of calling like the variable we use to represent complex numbers, just so we don't confuse things, we use Z instead of X typically. It's not a big deal, right? So we'd say Z equals A plus B times I. So all complex numbers have both a real part and an imaginary part, but A and B could have any value. They could be fractions, they could be irrational numbers, it could be like the square root of 2, A or B could be the square root of 2, or they could be 0. So the set of real numbers, if we said all real numbers are complex numbers, have you ever seen an I in a number prior to today? No, right? Because real numbers don't have I's attached to them. So for the set of real numbers, all real numbers must have what value for B if it doesn't show up? If that term never shows up, what must the value of B be? 0. Yeah. So one way we could describe the set of real numbers is they are just complex numbers that have the form A plus 0 times I, where A could be anything. A could be any real number. But the imaginary part goes away because B is equal to 0. Right? So we can just define this. That's all real numbers, that's true. Well, what else could happen? Well, A could be 0, right? What if A is 0? If A is 0, then you just get some number times I, and we call that a pure imaginary number, because the whole number is multiplied by I, the entire number, right? And so those would fit in this set down here. We call them pure imaginaries. So, it could be, B could be anything, but it's multiplied by I. And then you have kind of the quote-unquote the normal complex numbers, where neither A nor B is 0, where there's both parts. And that would be numbers like, well, let's make an example of, like, what if we said Z equals 3 plus 4I? There's a regular complex number. What's the real part? 3. What's the imaginary part? 4. Okay? Okay? Strange, but they're important. So what do we do with these things? We do lots of things with these things. Well, we're going to add and subtract them. In fact, let's do that first, just so you see that there's nothing scary about these. Here, let me do something real quick here. That's pretty scary. I'm going to show you, that's interesting. I'll show you this, that's called the Mandelbrot set. I'll show you that in a little bit. It's really amazing. Try this. So what if we've got two complex numbers? You have two complex numbers. Let's call them Z1 and Z2. So Z1 is just 3 plus 4I. Z2 is negative 2 minus 5I. How do I add them? What do you think? It's really simple. You probably already know the answer. We want to take a guess. Say it again.
Would you just put 3 plus 4I equals negative, or you add them?
We're just adding them, yeah. How would I add those up?
3 plus 4I minus 2 minus 1.
Yeah, you're right. So, I mean, I could write it that way. I could write 3 plus 4I plus this thing. But I can simplify that. I can get a simpler answer than just that. How'd you get that? Say 1 minus what?
1 minus I.
1 minus I is exactly right. How'd you get that? What'd you do?
I put Z1 into 3 plus 4I into Z1 because do that.
Okay.
Into that.
Then you put that one there.
Uh-huh.
But how'd you get 1? That's correct.
3 minus 2.
Okay, so what you saw there, it's nothing profound. What you saw is that I've got some like terms and some unlike terms there, right? All you got to do is treat the I like a variable. Imagine it's an X, right? The term with an I is different than the term without an I, right? Okay, so if I add up the real parts, they combine. Those are like terms. 3 plus negative 2 is just 1. If I add up the imaginary parts, positive 4I plus negative 5I, well, that's just negative 1I, right? That's it. Couldn't be easier. All you're doing is just adding like terms. Treat the I like an X. Okay, what would I do if I subtract these complex numbers? No big deal. We've done stuff like this, right? What did we do earlier in the year when we subtracted a quantity? What did we do with the negative sign? What did we do? So imagine there's a 1 there, right?
Yeah.
And didn't we just do this?
Yeah.
Right? We just distributed the negative sign? So that gave us 3 plus 7I. What do I get there? Positive 2. What do I get there? Piece of cake. Now I just add up the real parts. So 3 plus 2 is 5. 7I plus 4I. Done. Okay, no big deal. All right, how about, let's try multiplication. It's really simple. If I distribute a 3 here, you just did that. It's no big deal. You did it with a negative sign. What if I distribute a 3? What am I going to get?
Just 6 minus 33.
Done. Okay, the next one's a little tougher though. Next one, there's one thing we got to check here. It's not real hard. Okay, listen. I got to say, I'm contemplating doing a whole new seating chart in here. And right now, I'm pretty much 100% going to do it for Monday, unless you can convince me that's not a good idea. I'm seeing a lot of things going on back over there that just kind of aren't really People aren't facing the front of the room, that would be a bad idea, right? I'd like to see everybody like facing up here, legs forward. Where should your eyes be when I'm doing this stuff? Probably up here, that's a good idea. All right, so not there, that's, all right, let's try that. Okay,
Just convince you.
all right. So we'll have a little audition here for the rest of the period, and let me see if things can be a little better. And then if not, I'll maybe reconsider the seating chart, I don't know. Okay, so, what do I do here, do you think? I mean, this looks pretty familiar. Imagine the eye is an X. What am I gonna do?
Multiply by 5 by -3, right?
Okay, good, so I'm gonna distribute like I normally would, just FOIL it out. So 5 times -3 is -15. 5 times 2i, 10i, no big deal. Okay, what if I distribute the 6i? 6i times -3,
Ooh.
-18i, no big deal. Treat the I like a variable. Okay, and then finally 6i times 2i. 12i squared. Okay, that one, that's a little strange. Everything else was fine, but the I squared is a little strange. So let's think about this now in terms of what I is. If I is equal to the square root of -1, what do you suppose I squared must equal? Say it again? No? Now, you guys are making this too hard. Think what happens if I square a square root. What does it do? Cancels it. So what's left behind? -1. All right. If I square that square root, everybody agree? If I square the square root, I just get a -1. Okay? So I squared, that's a little strange, I squared is equal to -1. I could keep going. What's I cubed? I can just be tricky with this. I cubed is just the same thing as I squared times I, right? Because if I multiply like bases, I add the exponents. Everybody agree? I cubed equals I squared times I to the 1, because 2 plus 1 is 3. What's I squared? I squared is -1, so I get -1 times I is just -I. So I to the cubed is -I, or I cubed is -I. What about I to the 4th? Now we can be tricky with that one. I to the 4th, why don't we do it this way? I to the 4th would be the same thing as I squared, right? I squared is -1. What's -1 squared?
Positive I.
What's -1 squared?
Negative I squared.
See, I squared is -1. What's -1 squared? That's not hard. 1. How about it? Okay, so then now we got to move forward. What about I to the 5th? Well, wouldn't I to the 5th just be I to the 4th times I? But I to the 4th is just 1. So it's I. The cycle starts over again. You get that? I to the 5th, I to the 6th would be the same as I squared. I to the 7th would be the same as I cubed. You get that? Okay, so you tell me then, what is I to the 98th?
Oh my god.
You should be able to tell me. Yeah, think about it a little bit. It is -1. How'd you get that?
Yeah.
Whoever said that.
Come on, bro, I don't know.
How'd you get that? That's right.
I just said one of those three.
What'd you do?
I just said one of them and got lucky.
One of the 3 and got lucky? Okay. So there's maybe a better way. So you know that this cycle goes every 4 rounds, it's going to repeat. Agreed?
Yeah.
So every 4 powers. So I to the 4th would be the same as I to the 8th, right? Which would be the same as I to the 12th. So every multiple of 4 is going to end up there, right, at 1. So think of the multiples of 4 leading up to 98, right? 98 is not a multiple of 4, but 96 is, right? So I to the 96 would just equal 1, right? So I to the 97th would be starting the cycle again. It would just equal I, and I to the 98th would be the same as I squared, which is -1, right? So all you'd have to do is just see how many times, we have to know what the multiple of 4 is, like, right before that number. So I could ask myself, Does 4 go into 98 evenly? No, it doesn't. What's the next lowest number that it goes into? 96. And then because 98 minus 96 is 2, I know I'm on the second row of my pattern, right? No big deal. We don't really need all that to solve this problem, though. In this problem, all we're worried about is I squared. Well, that's an easy one. What was I squared? -1, okay? So whenever we get an I squared, all we're going to do is we're going to immediately just replace that with a -1. So what does this work out to be then? We end up with -15 plus 10i minus 18i plus 12 times -1 is just minus 12. So really, when you end up with a term with an I squared, all you got to remember to do is just change the sign to the other sign, the opposite. Okay? If we add those up, we end up getting -15 minus 12 is -27. 10i minus 18i is minus 8i, and we got it. Piece of cake. Okay, so multiplying complex numbers isn't even that hard. You just FOIL it out. The only difference that's not normal, something that you wouldn't expect, is when you get an I squared, you just turn it into a -1, it's a piece of cake. Okay, no big deal. All right, so then, here's the thing I do want to tell you about those. There's one other thing. These complex numbers are a little strange. How do we represent them? There's one way we can do this that's really useful. Not only is it convenient, it's useful. We put these in what's called the complex plane. What does it look like I'm drawing? If you didn't know any better, wouldn't you think I'm drawing the XY plane? Same thing. It looks exactly like it, but instead of the x-axis, this is what we call the real axis. And instead of the y-axis, that's the imaginary axis. So where do you think I would plot, in the complex plane, I want to plot a point corresponding to a complex number. What if I took the complex number z equals 4 plus 3i? Where do you think I'm going to put that?
4 on the real,
Okay, and
then 3 on
there you go. So the real part is 4, right? So all we're really doing here is just a plus bi, where a is 4 and b is 3, right? So that makes an ordered pair. So we're going to go over 4 on the real axis and up 3 on the imaginary axis, and there's the point with coordinates 4, 3. That's the one that corresponds to z. Okay, that's it. Say it again. Well, the I, so the I is what b is multiplied by, but all we want is just the b, okay? We're just plotting the values of a and b, okay? So what's useful for us to do sometimes, though, is to know how far that point is from the origin. That's a useful number when we're dealing with complex numbers. So a lot of times we represent that with a vector, which is just a fancy name for an arrow. It starts at the origin and it ends at that point. Now, if I want to know the length of that arrow, it's pretty easy. It's just a Pythagorean theorem, right? Think about this in terms of a triangle. It's a right triangle, and if this point has coordinates 4 and 3, what's the length of that side? How far did we move over? How far did the ant walk horizontally to get to there? Yeah, 4. How far do you walk vertically?
3.
So we call this the modulus, or the magnitude. It looks like an absolute value, and it's equal to, how would I get that length then? If that's 4 and that's 3, what's the length? Okay, it's the square root of a squared plus b squared, right? So it's just going to end up being the square root of 4 squared plus 3 squared. What's 4 squared plus 3 squared? 16 plus,
8 and 25.
okay, 16 plus 9 would be 25. What's the square root of 25? So the magnitude, or the modulus, would equal 5, right? So we could be a little better than that, though. We don't have to pin ourselves down to one complex number. We just know that for any complex number of the form a plus bi, the modulus, or the magnitude, is just the square root of a squared plus b squared, right? Yes, ma'am.
Why would we need to find the modulus?
Okay, here's why you need to find the modulus. Glad you asked. Okay, let's talk physics a little bit.
Yeah.
Yeah.
Talking about.
Okay, let's talk physics. Let's talk, when are we out of here? 40, good, I got time. Okay, good. So, we're gonna talk about the physics of electronics a little bit, circuits. So, you can break circuits up into different categories. If you could talk about digital circuits that are all over your computer, tiny little digital circuits, those act a little bit different. So we're not gonna worry about those. We're just gonna talk about analog circuits. Analog circuits, where would you find those? Your toaster, your car, all over your car. If you got a stereo, right? If you got a bumping stereo and it's got an amplifier in your stereo that's gonna be, that has to process, think what happens. You're inputting a signal that's the music signal. It's really a tiny signal, low voltages. And then your amplifier is gonna amplify that a bunch so you can drive speakers that send the sound everywhere, right? So an amplifier has analog circuits all over the place. They're everywhere. I mean, you can't swing a dead cat without hitting analog circuits everywhere. I mean, they're all over the place. They're in that box up there. They're in the microwave. They're all over, right? So analog circuits, let me give you a little tutorial on analog circuits. Analog circuits are all broken up. Every analog circuit is made of these three parts: resistors, inductors, and capacitors. That's it. So resistors are, what's an example of a resistor is your toaster, the elements in your toaster. So when you send electricity through the little wires on the inside of your toaster, what do? They heat up because they're resistors. That's what resistors do. Resistors resist the flow of current. When you push current through a resistor and you force it to go through the resistor, it heats the element up and the energy goes away as heat. So it's hard to push the current through a resistor because it resists it, right? Okay, so that's simple. That's what a resistor is. That's our electronics symbol for a resistor, just kind of like a zigzag pattern. Inductors are, you guys know what a slinky is? Yeah. That's a spring or a slinky is an inductor. So the wire, if you bend it into a coiled pattern, that's an inductor. When you pass current through that, strange things happen. I don't want to get into all the details, but kind of in a nutshell, when you pass current through that, the shape of the wire, the bendings in the wire, cause the current to sort of slosh back and forth. Because there's complicated things going on with the magnetic field and the electric field, and they interact, and it does some strange stuff. You can learn about it in physics, study physics. So that's one of the elements you can put in there. The other element you can put in there is called capacitor. Now, capacitor is, so imagine you've got this wire, copper wire, let's say, and we're going to cut the wire in two, and at the end of one piece of the wire, I'm going to weld it to a metal plate, thin metal plate. Okay, there's that piece. Take the other piece of wire, and I do the same thing to a second metal plate. I'm going to push these very close together, but not touch them. That's a capacitor. So usually what we do so they don't touch is we will put something in the middle that doesn't conduct electricity called a dielectric, which is just something that's an insulator, right, like rubber or styrofoam or something, right, so that the current can't pass through it. Yes, sir?
So like welding,
So yeah, in welding, you would be using tons of these things, exactly, right? You're controlling the parameters of the current and the voltage, right? And if on an arc welder, when you adjust the dials, you're adjusting essentially you're adjusting the strengths of the resistors and inductors and capacitors in the circuit. To make it simplify it. But yeah, it's a good question. So capacitors, it'd be pretty inconvenient to have these big plates. They take up a lot of space. So what we do with them instead is we make the plates out of foil and we cut them into little strips. So they're like long, skinny strips that are stuck next to each other, and then we just roll them up. So they look like a film tube or something, right? A canister. So if you look into a big stereo and you see, like if you ever look at the circuit board in a big stereo, you'll see these big black cylindrical, they look like an oil filter kind of, that's stuck on the circuit board. Those are just big capacitors. And what they do is when you send the current along, and it stores charge across the two plates, and the more charge you build up, the bigger the field between the capacitor plates, and you can release that when you need to have like a really high amount of current for a short period of time. You can close that gap and release some current. Anyway, there's a lot of specifics in there. Those are the three things that we combine in circuits, and that's it. So like here's how we do a circuit diagram. in a circuit diagram, like let's just look at this guy right here. Really simple circuit. So we've got some kind of a battery here, or it could be a voltage source other than a battery. But we've got some voltage source that's trying to push current through this circuit. Okay, that has to follow this path. So as the electricity or the current travels through the circuit, it's going to run across, it's going to pass through a resistor, it's going to pass through an inductor, and it's going to pass through a capacitor. Okay? Each of those is going to provide its own little bit of resistance to the flow of electricity. But the thing is, they interact in strange ways. They interact in ways so you can't just add them up. It doesn't work if you try. Like if the resistor itself, if taken by itself, if the resistor has a resistance of 3 ohms, and that's just a unit that measures how much electrical resistance is there. How much does this circuit element resist the flow of current? Well, the measure is 3 in this case. What about the inductor? The inductor by itself has a resistance of 5 ohms. So just pushing current through that inductor, it would be a little harder than the resistor. It's got a little more resistance. The capacitor, 6 ohms, harder yet. Okay, but if I add those all things up in a row, you'd think the answer would be 2 plus 5 plus 7 is 14. It's not. That's not how it works. They interact in strange ways. And it doesn't give us the right answer if we do this experiment. We measure the overall resistance of the circuit, which we call impedance. It doesn't work. I'm going to run out of time, aren't I? We had done in a minute? Okay.
30 seconds.
We'll pick it up on Monday, because I only got about 5 more minutes and I can explain this to you. All right, I'll put a couple assignments up you can be working on. Just adding, subtracting, multiplying complex numbers, piece of cake.